Thank you all for joining us today. We're excited to get into reducing manufacturing downtime using single gas transformer monitoring, and we're honored to have Andre speaking to us. Just some basic notes for this presentation. If you have a question, you'll notice that you won't be able to put your question into the chat, but you will be able to put it into the Q&A box. So at the bottom of your screen, there is a question mark inside of a chat box. If you click on that, you can enter in your question, and then Andre will get to hit your questions either throughout the presentation or also at the end of the presentation. Additionally, these slides and the recording of this talk from today are going to be shared with all of you. So don't worry about capturing or saving this information. We'll make sure all of it reaches you after the presentation concludes. And with that, Andre, I'll pass things off to you.
Thank you, Chris, and good morning, everybody. If you're on the West Coast, good afternoon if you're on the East Coast. Thank you for making this time available to spend with me. This time is your time, so this event is for you. As Chris mentioned, everybody will be placed on mute, so please do ask your questions in the chat. We'll answer what we can, and if we can't, we will get back to you with answers after the fact in a written form. Additional information is also available to you on a lot of the content and information that I'm sharing through the course of the day. And that would be available. You can go and find more information, or you can reach out to us after the event as well to get further insight into this. The topic for today is really about how we reduce your manufacturing downtime. And the tool that we want to talk about is the single gas transformer monitors. So this clearly applies to industries and organizations that are very sensitive to the availability of power, using transformers that you own and operate. I would like to cover just two things. I'm somewhat old school, and I tend to mix up the term oil and insulating liquids. I know that insulating liquids is the new term, but if I do mix it up and I do tend to use the word oil, please forgive me. And sometimes I may refer to the word fault as opposed to a transformer abnormal condition. Clearly, I mean roughly the same thing. I'm not referring to a fault on the electrical grid. I'm referring more to an abnormal condition. If you've joined us today from a utility, perhaps from an industrial entity, perhaps even a data center, the drivers that impact you every day are going to be more or less the same. And it's against these drivers and this economic and technical climate that we're going to present our information today. And clearly it's the first and most obvious one is this increasing pressure to reduce cost. You've got to get spend down, and everybody's very anxious to see that happen. There's an aging workforce. You have access to fewer specialized skills than you used to have. You may even have smaller workforces than you used to have. And your safety and regulatory environment is changing. These codes are changing. They're changing fast. NFPA just recently released an updated version of the code. And they're talking about more versions of the code coming out soon again. And the most important, I guess, is internally within your organizations, your personal performance criteria is around increasing productivity and perhaps some of the electrical availability KPIs that you're looking to get. So against that backdrop, and we really hope this doesn't happen to you, but I've put together something of a theoretical scenario, although for many it's not. You can imagine it's 5 o'clock, you're on your way home, it's Friday afternoon perhaps. The operations director calls and says the production line is down. And it's electrical. You get on the phone, you reach out, and you find out that a transformer, one that you own and operate, has failed. And your weekend just got cancelled. All those plans you had are gone. In the best case, you have redundant transformers, or you may have the capacity, you may have transformer capacity to reconfigure your main ties and get the plant up and running again. Your losses are high, but at least they're controlled. In the worst case, you need a new transformer, and the production impact is going to be substantial. And there may be a range of scenarios somewhere in between that you're trying to navigate. And the first question after you've sort of recovered from the shock is, what leading indicator could have predicted this failure? What could I have done to know that this was going to happen and to try get in front of it, as every responsible business person should be doing? And it's really important for the audience to understand what the true business impact is when this happens. And I will say, we've spoken to a number of customers, and while this is a theoretical scenario, it's actually closer to home for some. And as you look at some of the statistics, you'll see that it is in fact getting closer to home than you realized. So what's the real cost of an outage? And there's a number of sources for cost data. As you study all the different reports, you'll find varying projections of cost. Clearly, it's industry specific, it's capacity specific. But if you look, the average cost of a downtime is estimated to be about $9,000 a minute that it'll cost your organization. The typical outage duration for 45% of commercial and industrial companies ranged between 5 minutes and 59 minutes. And then as the transformer capacity increases, your costs can range anywhere from 100,000 to 50 million. I mean, that's the far extreme for the loss of a transformer in the 20 to 40 MVA range. So pretty significant costs. What you also see is that short interruptions, and by that the definition is interruptions less than 5 minutes, cost organizations an average of $50,000. But more importantly, the percentage of companies that experience outages lasting 5 minutes or more has increased from, less than 5 minutes, has increased from 20% to 40%. It's doubled. And so when I spoke about how theoretical that scenario was, it's actually getting closer to reality for at least half the organizations that were surveyed in this particular study. And some of these estimates, if you look at the footnotes, you'll see these are 2021. As I read more about what's going on, it's getting even, the percentages are growing even further. And we've spoken about the real cost of outages, but the one that I have left off because we don't have numbers and I haven't been able to find them is what it costs you to contain a spill. What if the transformer is ruptured? If there's a fire, what is the cleanup cost? Because those can be pretty substantial as well. Now, clearly, when we talk today, we can't mitigate all the outages. So that if there's outages that are beyond your control, perhaps the grid, it has a blackout and you're unable to source your power, you can't control that. But what we're going to focus on for the rest of the day are the items that you control. They're the items that you're able to influence and try get in front of. They're also typically the items that lend themselves to being the longest outages. And as you know from the numbers, the length of outage clearly matters. So your question for yourself is, how do I avoid that surprise? What is that leading indicator? And clearly it gets to the condition of the electrical assets. And when you look at at the key items in your grid, you're going to have bus bars, you're going to have power lines, you're going to have circuit breakers and transformers. And by and large, the condition of the asset, the bus bars and power lines, they can be inspected visually. Your circuit breakers may have I2T recorders, they may have trip counters, operation counters. They're also serviced periodically, so you can get in there and you can have a look at what the condition of the circuit breaker is. But transformers are unique. They have no built-in diagnostic capabilities whatsoever. You get a liquid temperature gauge, you get an a liquid level gauge, but there is no diagnostic light, there's no diagnostic condition as you buy that transformer from the vendor unless you've specifically asked for them, and they are not serviced unless a particular condition arises. And it gets to, you can't manage what you don't monitor. So you can't get that leading indicator with the system and your status quo as is. So to understand why that's really matters, let's just take a look at a few of the transformer facts. Firstly, transformer costs have increased 435% from 1985, but just since 2020, it's increased 65%. Lead times for transformers are still somewhere between 40 weeks and 90 plus weeks. If you look at it, this is courtesy of Virginia Transformers website, where they have published, this is as of yesterday, they've published the typical lead times. And it becomes rather obvious that we need our transformers to last longer. But I challenge the notion of, is that our priority? Because it's my observation in talking to people is what we really want from transformers, first and foremost, with these lead times and costs, is we don't want them to surprise us. Of course, we want them to last longer, but surprises are perhaps even worse than a planned replacement. Some other interesting facts for you. The oil volume per MVA is reduced by 66% since 1960. It means the design margins are shrinking, and the transformers we buy today aren't quite as robust. They are compliant, but they aren't quite as robust as the transformers we used to buy of old. Many people consider replacing transformers based on the age of them, but they aren't the primary predictor of failure. A 6-degree winding rise over 90 degrees will double the aging. A 1% increase in moisture will double the aging rate of paper insulation. So the primary predictor is not age, but perhaps the way it's been run and the way we're able to manage the transformer. We also know that incipient faults can lead to catastrophic failures. And for those who are not familiar with the term incipient, that means it's an abnormal condition that starts small, but continues to get worse over time. So it's not the big bang. I know there's a lot of press, the media love big transformer fires and a lot of those things. But transformers, many of the faults that we've seen are incipient faults that start gradually and systematically get worse. And if your organization is sensitive to its carbon footprint, we did a study, and replacing a transformer creates 12 tons of carbon dioxide for a 1 MVA transformer, and it can get as much as 1,600 tons of carbon dioxide for a larger 750 MVA transformer. So your ability to minimize your footprint depends on your ability to avoid a premature replacement of a transformer. So with that said, what are the most common transformer failure causes? What are the things that cause transformers to fail? And there are many more modes than this, but I've prioritized those that are identified in the priority by the IEEE and the CGRE working groups and studies. It's insulation deterioration, it's overheating, overloading, partial discharge, contamination of the transformer liquids, insulating liquids, elevated moisture levels, and mechanical damage, which may also include, perhaps if the transformers are somewhat new, the quality assurance of things like welds. There are many other failure modes, but I've chosen to focus for the conversation today on the active component, in other words, the transformer tank, the windings, the core, and the leads. The good news is that hydrogen monitoring can detect the early onset of all these potential failure modes. And to understand why I say that, let's dissect a typical fault in the main tank. Let's have a look at the fault. And for those of you that are old hands at transformers and participate in committee meetings, forgive me while I go through this. But I think it's important that everybody should understand the claim. I mean, what has hydrogen monitoring got to do with detecting a failure caused due to partial discharge, for example? So let's look first at this transformer. You're standing in front of your transformer. Everything looks healthy from the outside. Nothing looks wrong. The measured values, the oil level, and the temperature indicator suggest everything's normal. You look at the protection relaying flags. There's no events. There's no flags raised. The cooling system says it's operating well. Everything is doing just fine. But if you put your Spider-Man glasses on and you look with X-ray vision into what's going on inside the transformer, there may be the onset of an abnormal condition. maybe interwinding, compromise of the insulation. There may be some other form of abnormal condition, but it's there. It can start small, as we discussed. It doesn't need to be very big. Remember, incipient faults get systematically worse over time. But from the outside, there's nothing that indicates that you have that event going on inside your transformer. That abnormality will create heat within the transformer. That heat will cause the insulating fluid to break down, and it's that breakdown process that will result in generation of gases. And hydrogen, as we'll see in a moment, is the first key gas that's emitted. So as that abnormality heats up the surrounding oils, that insulating liquid will break down. Different gases are emitted. The first, depending on the temperature of the amount of heat, the temperature of that abnormality, we will emit gases. As the abnormal state progresses or is sustained, more gases will be created. Again, depending on the temperature, we'll have a look-see. And over time, we reach a state of equilibrium where these gases will dissolve. They'll either be in your nitrogen blanket or they will dissolve into the insulating liquid, and there'll be a steady state of this dispersion of the gases depending on the quantity, the volume. If we look at IEEE C57104, this is a standard that shows how and why and when different gases are generated due to the breakdown of the insulating liquids. And if you look to the graph on the left, you'll see the temperature increases from left to right. As the temperature increases, you'll see different quantities of the different gases that are generated. But what's important to note is that hydrogen is generated for all internal faults. We start picking it up at 150 degrees C, and it'll go well beyond the 800 degrees C. And it's often referred to as the first fault gas or the key gas, depending on the terminology that you'll come across. If you do look at this particular standard, you'll see all the gases that are generated will depend on the fault temperature and the type. And you'll be able to understand how the different gases that are generated, where they start, and they are typically associated because of the temperature, they're associated with particular failure modes. So in essence, what we're saying is that when that fault occurs in that transformer, when that abnormal state occurs, as it starts, including partial discharge, which is not temperature dependent, hydrogen will be generated. And as that hydrogen is generated, we're able to start doing something. We know that the abnormal state will generate hydrogen. So what to do? What should we do? What's next? And the answer to that question is very simple. If we were to install hydrogen-specific sensors on the transformers, typical example shown in this diagram is the H2scan's grid scan products, we can perform continuous online measurement of hydrogen. Clearly in the gas space, we can measure it in the gas space typically, but we can also measure it in the oil space. And today's monitors are not as simple as just picking up hydrogen. These small hydrogen sensors will also typically detect the temperature, so we can track the temperature of the oil or the gas space. We can also determine the moisture and pressure in the tank. So adding these sensors to the transformer will allow us to understand the hydrogen measurement in the tank continuously over the duration and life of the installed transformer set. Now I can imagine you're sitting there saying, well, we do periodic oil samples. We do it every year, every 2, every 4 years, maybe. Is that not enough? And I'm going to try and answer that question. I'm going to try and give you greater insight into that. Manual sampling, in other words, drawing of the insulated liquid, sending it to a lab for dissolved gas analysis is the norm, and historically has been adequate. But it provides a static concentration of all the combustible gases when the sample was taken. And that assumes no gas escapes from the syringe in transit. That assumes you've done that right, you've used the right containers. But it is a static measurement. Let me give this particular thought for you to consider. Delta X Research is a company with a very significant database of performance data of transformer failure and gassing data. They use that same data in their algorithms to determine and to produce key metrics to help you understand what the transformer's behavior is likely to be. And Jim Durkheim has said and observed that most transformer faults will migrate from the start of gassing, in other words, that first point, to a failure in less than 6 months. If you're doing annual samples or biannual samples, you may detect that start of or the onset of that failure. But if you're in the wrong window, you certainly are likely to miss that. But there's another element to consider. If you're recording the hydrogen data perpetually, if you've got continuous online monitoring of that hydrogen data, you start to get the trend information. And we're going to look at 3 different real-life scenarios of how hydrogen trend data has assisted the customers. Each of these is real-life samples of data. The first on the left shows the hydrogen production. It was sudden, it ramped up, and over time it dropped off. It subsided. And so now not only did we know we had the production of hydrogen, but because we've got trend data, we know that it dropped to 0 and that no further action was required. We'll keep an eye on it. We certainly want to record it because this is typical of a through fault. And we know through faults are a cause or certainly a contributor to the failure of transformers over time. But because we had the trend data, we're able to assess that we're able to get an insight into what probably caused the failure and whether action is required. And clearly no truck roll, no outage, continue business as usual. The second transformer, although you can see the hydrogen production levels are very high, the gas level is very steady. And with it being steady, there's no immediate action required, although this transformer certainly would benefit from degassing. We will also, because of its level, we'll put it into a watch mode, or we'll put it onto the watch list, and we'll keep a very close eye on this transformer to make sure that the rate of production doesn't change over time until we can get that transformer degassed and cleaned up, perhaps with new insulating liquids put in. Now, this pattern is typical of high harmonic transformers typically in renewable locations or locations where there's a significant amount of harmonics. If you know transformers, you'll know that harmonics do tend to cause transformers to heat. It's the heat that causes the fluids to break down and generate the hydrogen. The third one is a classic example. We see a sudden and rapid rise in gas. Your next step is to do an immediate manual DGA. Get the sample drawn, get it to the lab. Your immediate next step is not to call the vendor and tell them that their sensor's broken, as is more common, but it is to do an immediate manual DGA. And this is a more classic example of a typical fault onset. So at this point, we know something's going wrong. We know something is not normal within the transformer. And if you're doing the multi-gas DGA manual sample, you'll be able to look at the different concentrations of the gases to give you insight through the Duval triangles as to what the root cause is and what your next action should be. So hydrogen monitoring is the leading indicator. It alerts you to the presence of an evolving condition. It will help you understand the severity of the fault condition, and it can certainly guide your next steps. So to get back to the question, is manual sampling not enough? Yes, it is historically good. It does work, but it also has shortfalls in that it's static. It's got large windows where you have periods of unknowns, and you certainly don't get trend data. You certainly don't get any leading indicator information from the manual DGA. But once you've identified that something's happening within the transformer, it is one of the most crucial next steps for you. So I'm going to recap very briefly some of the technical content of what we've gone through, just to wrap it all up for us on a technical consideration. We've established that transformer faults or abnormal conditions create heat. That heat will convert the insulating liquids to gases as that breaks down. The hydrogen is generated by all the fault types, from 150 degrees C all the way actually beyond 800 degrees C. And hydrogen is the first fault gas or key gas that is generated in the transformer when you enter that abnormal state. A single gas, and by that we mean hydrogen monitor, will detect changes in the transformer condition in real time for you. It'll provide context, and by context I mean the trend data, to guide next steps. And they're very cost effective. They are small, they don't have moving parts, and they're not over. The fact that they're only monitoring the hydrogen allows them to be very reliable. The lab analysis of manual samples will detect changes in the transformer, but at 1 to 4 year intervals, it may be too late. You certainly could miss the transition from first gassing to failure. You have no visibility between the samples, and it may lack the context as to what, if you suddenly see there's a hydrogen in the sample, was it a through fault? Did it pass through? Is everything fine? Is it not? Do you need to take action? Do you need to watch the transformer? That context is typically not available from manual sampling unless you really bring the manual sampling frequency in. It's worth mentioning that multi-gas dissolved gas analyzers, I'm talking about the online systems, they do work for online measurement. They certainly do. In fact, they provide a significant more information on the other gases. But the cost to purchase and maintain these normally restricts their use to larger transformers. So typically utility scale type sensors, whereas, as I mentioned before, the single gas monitors are particularly cost effective, especially on small transformers. And I like to say, and I like to think of the online hydrogen sensor is the most effective transformer diagnostic tool that you can get. It's not, if I had a dollar for every time somebody called them a smoke detector, I'd be quite wealthy. They are not. Clearly, they're not binary. They don't just give you a value. They give you a lot of insight. They give you a lot of insight perpetually. But they are, by all accounts, the modern version of a check engine light in your transformer. It'll guide you on next steps and severity, and it'll give you insight into how your car, or how, in our case, how a transformer is behaving. Now, we've covered the technical aspects of how transformers give you the actionable insights, or what I like to call the leading indicator on the condition of your transformer. And if you know that, you're able to plan for it. The more you're able to plan for it, you're able to avoid, to the extent that you can, unplanned outages and try and meet some of your KPIs. And we've covered that pretty well, but there's 5 good reasons. There's actually many more, but I've picked the top 5 for you as to why online key gas monitoring is good for your business as a whole. We've covered the first one, but the second is it saves money for your business immediately. And we'll look at each of these a little bit further, but the return on investment for hydrogen monitoring is compelling. It's self-funding. Think about some of the costs that we presented in the earlier slides and what a 1 hour outage may cost you. It defers your capital expenditure. It will reduce your maintenance spend, which gets to your industrial climate says, hey, I want to spend less money. I've got fewer people to work with. They're cost effective. You don't have to put monitors to monitor the monitor. They can be installed on your entire transformer fleet. They are that cost effective. And most importantly, your time to value is immediate. There's no long drawn out projects, and we can cover that in a little more detail. We spoke a little bit earlier about your regulatory environment changing. Online monitoring will aid your transition to the new NFPA 70B code compliance, and by association will increase and improve your personnel safety risks that you face. We'll talk about how it can improve your insurance premiums, or at least perhaps the deductible. And we covered earlier, I'm not going to revisit this one, we covered earlier how avoiding the unplanned outage of the unplanned replacement of a transformer will significantly reduce your carbon emission and contribute to those corporate objectives if you have them. So let's talk about the economic benefits. So first, you will improve your capital spend. You're going to avoid unnecessary transformer losses. If of those losses that we've identified, those loss causes, you'll be able to identify and correct faults before damage is irreparable. If you can save a transformer and get it repaired, it is so much quicker than waiting for a new transformer. And on your right is a real true life case study for you. This transformer triggered a hydrogen alarm. They pulled the manual DGA information, and the manual DGA suggested that we had arcing. The transformer was inspected and a loose nut found. They were able to repair the transformer and return it to service pretty quickly. More importantly, you'll also be able to replace transformers in your refurbishment plan based on condition and not years in service. So you'll be able to get to the transformers that are the most likely to fail proactively. You also get improved maintenance spend because you'll focus on the transformers in need. You get improved workforce utilization because you'll now work on, again, transformers in need. And we spoke earlier about spill mitigation. If you have a spill, if there's a fire, if your fluids leak, depending on where you are, those costs can be mitigated because you're able to take the transformer out before there's a catastrophic failure. I mentioned earlier that it will assist you with the NFPA 70B compliance. In 2023, the standard was converted from a recommended practice to what is now standard, and they changed a lot of the language from should do to shall do. And NFPA now requires continuous monitoring, and what we mean here by continuous, it's periodic is still certainly a candidate for it. It doesn't mean online, but it's continuous monitoring to determine the maintenance levels for the maintenance that's still required. But what it does state as well is that predictive techniques such as continuous online monitoring is permitted. So using your continuous online monitoring to dynamically adjust and set your maintenance windows is permitted within NFPA 70B. And not only does it, so it solves the problem of doing that, it also solves the problem of performing the continuous monitoring, whether it be manual, whether it be inspection. So it addresses the standard for observation. It will reduce the risk of fines or denied insurance claims if you're not compliant. And if you're using a system to collect, to collate, and to store the continuous online hydrogen measurements, as we'll show in a later slide, you also address the NFPA requirements for documentation of the information you use to determine your maintenance intervals. Then there's the potential insurance benefits. This is the second to last benefit, in addition to all the technical aspects. FM Global is a major insurance company, and they generated or created a standard 6528 for online DGA systems for liquid immersed transformers. FM Global will also certify sensors that meet that standard, and they'll allow you to put the FM Global approved diamond on it. So our recommendation is to look for monitoring solutions with the FM approved diamond marking, and then discuss the potential savings with your insurance carrier, especially if FM Global is your carrier. But beyond that, even if they're not, think about this. The industry that is the most invested in your transformer not failing, the insurance industry, has written a standard that defines the requirements for what they think will assist you in avoiding that failure. So anybody's product that conforms or complies to that standard is probably something that's good for your business, because that means the folks that are the most invested in a successful and viable product have defined what it is, and they've certified that it meets their requirements. And then your last benefit. As time evolves, you move from the reactive maintenance, you want to get to preventative maintenance, which is perhaps where most people are today. But ultimately, you want to get to predictive maintenance, where you're able to use machine learning, where you're able to use pattern recognition. And the reason you want to do that is many companies have seen unplanned downtime reduction from 50% to 40% reduction in their maintenance costs when they go to predictive maintenance. And if you recall, we spoke about the requirement to get more done with less money. Continuous and online monitoring of transformers can form the basis for that condition-based monitoring and maintenance, and will effectively reduce the unexpected catastrophic failure. So if you're monitoring your hydrogen perpetually, as we showed earlier, in your transformer fleet, you're able to transition to predictive maintenance in the future, sooner or later. It depends on you, and it depends on your ability to store that data, because that's a critical part of it. But the sooner you start, the better. I've always said that tomorrow's winners are the people that are collecting the data today. So the shift to predictive maintenance is that fifth benefit to transformer online monitoring. So in summary, your weekend went up in smoke. And the first question, well, the question you asked once you understood what the problem was, how can you get a leading indicator? Clearly, single gas transformer monitoring is the leading indicator. It will reduce your exposure to transformer-related production interruptions, and it provides these significant additional benefits. It will avoid those costly power outages that impact your organization's production and revenue streams. It'll avoid potential environmental cleanup charges. It'll improve personnel safety. You'll know that if a transformer's got a lot of gassing going on, you won't allow anybody to get close to it or work on anything unless it's taken offline. It's cost effective across the full range of transformers in your fleet. It'll reduce your spend because you'll direct your financial and your human resources where it's most needed, as opposed to based on an assumption, age, or cycle. It'll help you get to NFPA 70B. It's expected to deliver insurance benefits, and it supports, the new word is digitalization. I preferred the term smart grid. I think they're more or less the same to me, but are clearly not. But it does deliver reliable and actionable information. And most importantly, it's very fast time to value. We're able to install these on a live transformer. You're not required to take the outage. On a transformer, of course, that does depend on your work standards. It does depend on the proximity of the drain valve. These sensors are installed on drain valves. And it does depend on their proximity to conductors and to bushings. And if you're installing it on the top of the transformer, yes, you will require an outage, but it's very brief. There's not a lot of mechanical or civil works required to install these products. If I may, I think I've concluded the technical and the commercial aspects of the reasons and how we can help reduce losses and outages within industrial environments. If I could just spend a few minutes talking about the sponsor, it's H2scan. H2scan builds hydrogen sensors that are built into most transformer OEM solutions. That was a legacy. That's what we did. It's 22 years old. In fact, this year we will turn 23 years old. We've been supplying service and supporting our customers for 22 years old. The technology started out of Sandia Labs and is now, the company is a global operating enterprise. The sensors are, it's a non-consumable, non-wear-out sensor. So just to help people understand it, the element that would normally wear out in a typical, the physics package, one may call it, comes with a standard 10-year warranty, just to demonstrate our belief and commitment to the fact that it never gets consumed and it never gets worn out. Our sensors, we have today over $1.3 billion of sensor hours in service. And inside transformers alone, 700 million transformer sensor hours. So we have a very large installed base of these products, and they're very reliable. We've accumulated such a significant body of knowledge over the years, and they're deployed very, very widely. When we talk about our sensors, I'll be very brief. How do we help customers reduce their downtime? What is it that customers look to us to help them with? And the products that we typically use, there's two of them as sensors, are the H2scan 5000 and 6000. They're very accurate temperature and hydrogen liquid or gas phase sensors. You can install them in either. The larger 6000 also includes a moisture sensor and pressure measurement. They're designed for 20-year life. The sensor element, as I mentioned, has a 10-year warranty. They have, and this is perhaps one of the most important attributes, they have auto-calibration. So these sensors will auto-calibrate themselves to eliminate drift. They do not require calibration over their operating life. You will never need to take them out. You'll never need to go to site. You'll never need to do anything. They self-calibrate as they go through their process in life. They come equipped, ready to connect into IoT, into your SCADA system. They support the Modbus and DNP protocols. And very importantly, they're FM approved for transformer hydrogen applications. They're clearly very compact, and they're very robust, and they're designed for harsh electromagnetic and outdoor environmental conditions. And they're easily installed. As I mentioned earlier, the average installation time is 1 to 2 hours, and it can be done on an energized transformer. So it's not very difficult for us to install this. You can go to site. Again, it is governed by your standard work practices, the proximity to conductors. So you are looking to do something very safe. Bringing this all together, it's one thing to have the sensor. It's another thing to focus on the data and what to do with the data. So we clearly have options that we provide our customers to help them. We have a resilient cloud-based data collection, a data processing, and a data storage and display platform. It's the H2 Cloud is the platform in the cloud that will store, present, and process the data. And then the Sentinel is the modem, the IoT platform. Magnet mounts onto the transformer and pushes the data to the cloud. The cloud will send alerts and fleet status to you as you need by email, text, or just simply online. Being a vendor management platform, everything's seamless to you. It's seamless software improvements and maintenance releases. It scales. You don't have to buy any infrastructure. You don't have to buy a server. You don't have to buy software. You don't have to do anything. There's no upfront infrastructure costs. The modems, this Sentinel modem will transmit data over a cellular network to the cloud application, and it's completely independent of your IT network. So we're not concerned about creating risks or cybersecurity holes in your IT network or OT network. And we've wrapped a lot of cybersecurity around making sure that there's integrity of the data on the move and data when it's static. And another important consideration is that these modems include a power quality monitoring option. You may recall earlier I spoke about power quality is harmonics, which is part of the power quality monitoring. Harmonics are one of the key contributors to heat in transformers, and they create a lot of gassing. Knowing that, being able to tie in the hydrogen with the harmonic measurements is a significant benefit to you. And if you're not sure about the harmonics, just think, harmonics are generated by, if you've got a lot of switched mode power supplies, think a lot of chargers in your factory. If you've got a lot of variable frequency drives, or if you've got your own connected renewable sources of energy, they all create a significant amount of harmonics. In my experience, harmonics are often misdiagnosed as a transformer's is undersized, or the transformer's design is poor or built poorly, when in fact it's just the presence of a lot of harmonics. So understanding the presence and the magnitude of harmonics is very significant. It's a very significant benefit to you, and it'll be able to help you understand why your transformer is gassing if you're able to correlate it to harmonics. and this sensor will bring that same data back to the same cloud application. So with that said, that's what I have. I've shared with you at the high level a lot of information, both technically and commercially, why hydrogen monitoring is good for your business, why it can help you reduce your unplanned interruptions and save you a significant amount of money on your production lines. But clearly, there's a lot more detail that's to be provided. So if you would like more, before I go into the Q&A, please feel free to reach out at any time. We can share more information with you. We can provide more explanation to you, and we can assist you with any other questions that you may have. So with that said, I'm going to look at some of the questions I've received.
I have some for you, Andre, if you let me just ask them for you.
Okay.
We have one question, which is, what is the warranty and expected life of an H2 scan sensor and transmitter?
Okay, the standard warranty on that particular product is 1 year. We as standard, the MTBF is 10 years on that product, and the expected life is 10+ years. We do have option for customers to purchase longer warranties. It depends. We didn't want to burden every single customer with the long warranty, so we've priced it that lets people decide which way they want to go. But the MTBF on that particular product is 10 years, standard warranty 1 year, with the option to increase.
Great. Can the H2scan sensor be installed on existing transformers?
Absolutely. Absolutely. In fact, the most common use case we have seen today is to put it on existing transformers. And that's why I mentioned the fact that you don't even need to take the transformer offline. You don't need an outage, depending again on where the sensor is installed. You simply go up to the transformer, you mount the sensor to the drain valve, you open the drain valve, you bleed any air bubbles out, you wire it in with the pre-made cables that we provide, connect it to power in the transformer cabinet, connect it to a communication device or to a display or whatever it is that you want, and you're up and running within 2 hours. It's not necessary to have these done at the factory. It's a very quick and very simple process. Again, I always stress this, governed by your own operating, your own standards for work and operating work instruction guidelines.
Awesome. Does the owner maintain and monitor the gas level, or is it monitored online by H2scan? And if it is monitored online by H2scan, is there a monthly subscription fee involved?
Yes, so we've tried to make the system as simple as we possibly can and as flexible as we can. So the sensor itself is sold as is. It's a one-time fee, and it will talk Modbus and it will talk DNP. So if the owner of the sensor wants to take it into a SCADA system or into their own monitoring system, as long as they can talk one of those two protocols, they're able to do that themselves. There's no subscription involved in any shape or form. If you elect to put it into the H2scan cloud application, there's only a monthly subscription associated with that. So the data will come to the H2 cloud application, and the owner of that asset will go into the cloud using their standard web browser interface and is able to set it up, observe the data, extract the data, recover the data. When we say monitor the online, we don't have somebody specifically looking at the data at this time. So nobody's sitting looking at a screen waiting to see if anything alerts are created. The nature of this, it's not that fast, it's not that dramatic, but the cloud application will push alerts to whoever's designated by email or text.
Awesome. All right, one moment.
And just to clarify, the H2 Cloud does come with a monthly subscription fee that commercially can be bundled up to cover an extended period if that's more convenient for customers.
How does monitoring with H2scan differ from using furan sampling when determining, your transformer replacement strategy?
I'm not familiar with the Fourier sampling, so I'm sorry. What I can do is I can get with my team. We can have a conversation around it, and get you an answer after the event.
Great. Can you briefly speak on the software monitoring and the web interface?
Let's speak on the software side of the monitoring and the web interface. So the data is sent over your classic, maybe it's Verizon or AT&T. It goes to a cloud application where the data is stored to access the information. And so that data will be stored when you in the cloud. All your data will be stored there. You remember I spoke briefly about storage is a critical part of it, both for your NFPA 70B, but also for your evolution to predictive maintenance. If you want to see the information, as you want to get insight, you'll log in, you'll go into your Internet Explorer or Chrome or whichever platform you like. You'll be given a URL that's very unique and specific to you. You'll have login credentials and you will go into that. That will, let me get here, that will give you access to a screen that looks something like the one on the right. You'll be able to see the assets on a map. You'll be able to see information about any particular assets on the left, and you'll get a number of graphs that will show you levels and trend information. So that will be available to you. You'll be able to navigate going from the high level, going down. You'll be able to navigate to look at particular gassing information. You'll be able to navigate down to look at harmonic and all the power quality indicator information that's available to you. And so you will navigate from that. And this is where you would set up the softwares, the need for software, the need to alert you. So you're just using public internet. It's secure, your standard with your standard security to access the software remotely. And because you're going in through a browser type interface, we are not concerned about the platform. It's a multi-platform.
Do H2scan sensors only measure dissolved hydrogen?
Do H2scan sensors only measure what?
Dissolved hydrogen.
They measure dissolved hydrogen and dissolved hydrogen and moisture. Correct. That's all we do. We don't do the other gases. We're not a multi-gas in the sensor.
Great. How does the sensor auto-calibrate?
If you remember, it's difficult for me to answer it because it's somewhat proprietary. There's a lot of wisdom in it. If you remember, we have some 700 million operating hours and 1.3 billion hours in total of sensor information. And the sensor is able to, we use a lot of AI and a lot of wisdom in our ability to auto-calibrate. And I'm gonna have to leave it at that for now. In this conversation, I am happier to have a slightly more detailed conversation with a smaller group of people. But it is truly the most valuable intellectual property asset that we own.
Great.
So we are cautious.
Absolutely. Can the H2scan feed into a BACnet BMS system?
So this particular product that you see today does not talk BACnet today. It's just pure Modbus for RS485 or DNP3. We also have a product, it's very similar in nature, that is designed for battery room environmental, what we call area monitoring in battery rooms where there's where gases are given when batteries are charging, or in energy storage systems. We are adding back the BACnet protocol to that product. It could be used it could be added because the platforms are so ubiquitous. We could add it to this platform. I think the estimated target date for BACnet is probably around July, August. But as of today, we don't have that. We do have a mechanism to convert the hydrogen levels to analog, 4 to 20 milliamps, if that's required, if that'll help in the interim.
Great. So On one of the sides of the H2scan scanner that you showed, let me see if I can understand this question correctly. On one of the slides of the H2scan sensor was shown on both the bottom and the top valves. Do I need two sensors? Can I measure H2 in gas?
No, you don't need to, not at all. I just showed it to demonstrate, I just showed it on that particular graphic to demonstrate that it can be installed in gas or it can be installed in oil. That is correct. So you can, yes, if you elect to install it in the gas space, one sensor is all that's required.
Great. And how many sensors can be connected to one transmitter?
At this moment, it's a one-to-one relationship today, and we're busy working on a meshed radio system so that we can connect all the sensors in the substation to the one transmitter. But as of today, to get up and running immediately, it's a one-to-one relationship. That same modem also provides the power that these sensors require, and so that's some of the work we're putting into the mesh radio as well.
Great. What is the frequency of auto calibration, and how are you notified if auto calibration was not successful? Can you trigger a calibration?
Okay, the frequency of auto calibration in the product you're looking at today is once every 12 hours. It takes place once every 12 hours. It is currently not designed to be triggered by the customer, by an external party or by a customer. It's because it looks at the drift, and it's sort of a moving. It's a moving point. It looks at a particular amount of movement, and when it sees a certain amount of movement, it will self-trigger the auto calibration process. If it's not successful, these sensors do have a diagnostic registers, and it will notify you through the diagnostic register that there's an alarm. I personally have never heard of it fail, but should it not happen, there's a Modbus or a DMP register where we pick up the diagnostic information.
Great.
And you'd be alerted that way.
All right, so we're going to wrap it up now because we just hit the top of the new hour. Again, if you have further questions for Andre, you can reach him using the details that are here in the presentation slides that will be shared with you. Again, we're going to share the recording and the slides with everyone. And thank you all for joining us today.